All right, so I'm going to be doing a sample problem involving systems and how you can solve a problem when you have a system with a pulley with mass. So the first thing we want to do when we're looking at problems with systems is we want to make sure that we write out all the net force equations that we know to be true. So the first thing is we know this 10 kilogram mass and this 2 kilogram mass are going to be moving. So based on just typical observations, we can set a direction of motion that's positive in this direction. All right? The next thing I want to do is I want to consider what's going to be happening along those axes. So let's first start with this 2 kilogram mass. We're going to assume that this surface is a frictionless surface. So the net force that's acting on this 2 kilogram mass is going to be M times A. And that is going to be equal to the net force, or the sum of all the forces. In this case, we're going to say this surface is frictionless. And for that reason, the sum of all the forces is actually just this tension force acting on the 2 kilogram mass. All right? So I'm going to label this mass 1 because that helps me kind of distinguish between masses and tension. So we'll call it mass 1 and force of tension 1. So we're making this problem a little bit easier by just saying the force of tension is the only force that's going to be pulling that pulley, or that's going to be pulling that box, excuse me, to make sure that we understand how to set these problems up. The second force equations that we're going to use is we're going to look at the sum of the forces acting on this 10 kilogram box. So for this 10 kilogram box, we're going to call that mass 2, and we're going to set that equal to mass 2 times acceleration is equal to, it's got a force of gravity pulling it down, but we set our axis here saying the downward direction is positive. So I'm going to say my force of gravity of box 2 minus, and it's got a force of tension pulling it up. So minus my force of tension 2. When you've done these problems when we did not know about a pulley with mass, the thing that we could do is we could just say these two tensions are equal. But the important component here, now that this pulley has mass, if these two tensions were equal, that would mean that there was zero net torque acting on that pulley. And so the pulley wouldn't spin, and that would mean you could put a 10 kilogram box and 2 kilogram box here, and you would see no acceleration. That would be odd to witness. So for that reason, we know that the net torque has to be positive, or in the positive direction, or the clockwise direction in this case, for the pulley. And so that is the third set of equations we're going to use. So these first two should be familiar to you based on your understanding of systems that you've probably seen before when you had a massless pulley. But now that the pulley has mass, it also has inertia. So we're going to label that pulley. And we're going to say, well, the pulley, well, we have rotational mass, which is inertia, and we have angular acceleration, which we represent with alpha. So we have inertia times alpha is equal to, now it's not the sum of my forces, it's the sum of my torques. So I'm going to say, well, I have a force of tension that's providing a torque on this pulley at a radius r, so it becomes force of tension 2 times my radius r. And then I say, well, it's minus my force of tension from mass 1 because it's pulling it the opposite direction against its motion. So force of tension 1 times r. And lucky for us, this radius is the same here. There are some instances you might see in practice problems where you have a pulley attached at different points along that. In this case, we're going to leave these radiuses the same. And if you see them at different points on the pulley, the easiest thing to do is to just state them in terms of r still, so you can keep one variable here. So if it was half as far, you would say 1/2 r, things like that. just to make sure that you're keeping one variable. Otherwise, it gets a little bit difficult to cancel stuff out and to substitute values where you want to. So, now we've got three sets of equations that we know are true, but they're not very useful to us still. The thing that we want to make sure that we're doing is we want to make sure that we get everything in the linear values. So I want to just convert everything to linear values just so I can do some substitutions. You could potentially go into your angular values and convert everything into angular values, but to make it into linear values gives me a better idea in terms of this acceleration, and then I could convert my linear acceleration or translational acceleration to a rotational value by dividing by r if I wanted or if the problem asked me to. But for this case, I'm going to convert it into a linear value. So my moment of inertia, we're going to say this pulley is a uniform cylinder. My moment of inertia is 1/2 mr squared. My acceleration turns into a over r. And remember, a and alpha are two different variables. A is your translational acceleration. Alpha is your rotational acceleration. And then I'm going to set that equal to ft2 times r minus ft1 times r. Now, we're going to do some algebra right off the bat to make this a little bit easier. I'm going to say, well, what happens to this r squared and r? Well, if I divide r squared by r, the squared goes away, and I'm left with r. But there is also an r in both components of this side of the equation, and it's on this side. So those r's are going to cancel out as well. And again, that's just some simple algebra that helps us illustrate that. So now I'm left with an equation, 1/2 ma equals ft2 minus ft1. So here's what I need to do next. I need to start figuring out what ft1 is and what ft2 is. So I'm going to rewrite these equations in the form of ft1 and ft2. Luckily, in this case, ft1 is already written for me. It's already simplified as much as it's going to be. ft2 I need to rearrange a little bit. So I'm going to get rid of this. Hopefully we all understand how I got to this point. And what I'm going to do is, just to make sure ft is positive, so it makes it a little bit easier substitution-wise, I'm going to add ft to this side. Let's use red just to make sure we keep our colors consistent. I'm going to add ft to this side, and then I'm going to subtract m2a from this side. So it becomes ft2 equals fg2 minus m2a. Boom. Now I can plug this value in for ft1 and this value in for ft2. So let's do that. I'm going to bring it over here on this side. So I've got 1/2 ma equals fg2 minus m2a minus, because ft1 is equal to m1a, minus m1a. So now I can rewrite some stuff. fg2 I can rewrite as m2 times g, and m2 and m1 are known values. So I know m2, I know m2, I know m1, and I can solve for a, because I know what all my variables represent now. The only variable I'm missing is a. So I'm going to go ahead and do that. Let's add m2, or let's substitute our values out. I'm going to use 10 for g, just because it's an easier number to use, and we're just talking theoretical here to help us solve our problem. So it becomes m2g, which was, m2 is 10, so that's 100, minus m2a, and m2 is 10, so 10a, and then it becomes m1a minus 2a. And so this mass, this is the mass of the pulley, because the pulley was what was spinning, And so that is 1. So it just becomes 1/2 a equals 100 minus 10a minus 2a, which then you add 2a and add 10a, so it becomes 12.5a equals 100. Divide by 12.5, and you find your acceleration to be 100 divided by 12.5, which is 8. Probably should have done that in my head. 8 meters per second squared. And what direction is that? Well, we set this as the positive direction. We ended up with a positive value, so we know it's going to be accelerating that direction, down with the 10 kilogram mass. And just observationally, you know that that was probably going to be the case. To find any other force of tension, I can just take my acceleration and go plug it back in to any of these equations and solve for a force of tension. And again, you should get a larger tension here because this torque has to be larger to make it accelerate in that direction. So thanks. Hopefully this was helpful in terms of solving systems problems with a pulley with mass. Have a good one.